Hello, good evening. Welcome to our first lecture in the Tecnoglass series this year, 2023. I'm Rudy El-Khoury, Dean of the School of Architecture. Let me start by actually thanking our sponsors, Tecnoglass, who have been supporting our programming for 8 years now, and they allow us to sustain the level of excellence that we always seek. Also, I remind you that you can, if you are a member of the profession, that you can get your continuing education credits by emailing Steve Fett for the validation. We are delighted tonight to welcome Matthias Kohler and Fabio Gramazio, who were among the first to introduce robots in the field and to pursue their potential in their own professional practice, but also especially in the robotic fabrication lab that they set up at the ETH Zurich, their home base for teaching and research since 2005. In the last 2 decades, they have integrated computational design, robotic fabrication, and material processes in radically innovative ways in pursuit of a new aesthetic sensibility in an emerging architectural territory. In their pioneering text, Digital Materiality in Architecture, that's 2008, and the Robotic Touch, 2014, they propose a new paradigm in architecture in which 2 seemingly distinct worlds, the digital and the material, converge to create new building practices and techniques. Their work ranges from full-scale buildings to art installations that have been displayed at the Guggenheim Museum in Bilbao, the Venice Architecture Biennale, the Vitra Design Museum, just to name a few of the many prestigious venues. For example, Semiramis, one of their latest pieces, was designed and robotically fabricated by means of human-machine interaction and AI-generated forms that negotiate complex material and fabrication parameters. The Immersive Design Lab is their latest institutional initiative, an extended reality platform for interdisciplinary research and teaching in fully immersive environments. We are very curious to see what that looks like. So please join me in welcoming our guests tonight.
Thank you very much. It's a pleasure to be here. Thank you for the introduction. Nice to be in Miami. Been here around 35 years ago, so feels like a late return. It's great to be here. Also, welcome to our guests on Zoom. It's February the 1st, 2023 for the record, because this is going to be eternal data, I assume. We would like to start our lecture on the topic of digital materiality in architecture, which is really about the coming together of, the culture of the digital and the material practice of architecture. We would like to show you projects which basically have a variety of approaches towards how these 2 domains actually meet, merge, dovetail, and create something new for architectural design. Let me start 20 years ago with this little Nokia phone. This was the first programmable mobile phone that existed. So it allowed you to program little codes, basically apps. It is, I think, 4 years before the iPhone got on the market. And we thought, this is exciting. So you have something, you have a device in the palm of your hand. And at your fingertips, you can design information. So we were inspired by this and wrote a little program which allowed you with the thumb to design a table. It worked like this. You could basically move a cursor with the joystick and press with your thumb. And by pressing with the thumb, you would actually push in the lower surface through the upper surface up to the point to where you create a hole in the table. And then you could send your design over the internet, and it would basically create this table for you. As you could see, you could also choose the color, you could choose the size of the table. Now, what's interesting, the data which is sent looks very simple. It's a few numbers. You see here the author's name, Mike in this case. You see a roll color, so color code. You see the length, width, and heights indicated by L, W, and H. And then you see these basically 7 points which are indicated with the pressure data of where the human put the cursor and how much force it applied. So very straight on. That's what you've been inputting. That's sent to the server, and the server then recreates this surface, which is a distorted, doubly curved surface, which expresses this human touch in a digital domain. This data directly goes onto a CNC mill, which then transforms the physical material by removing this timber. And it results in a table, the M table, the mobile table, or the table designed on a mobile phone, which has these features of basically material loss in a way, where you see it has these very thin edges outside on the border of the table, also on the table surface. It has this quite delicate landscape underneath. We then produced a kind of poster where you can see on how this entire process is supposed to work for a potential client. Of course, you can imagine this wasn't a huge commercial success. This was really a prototypical project for us on mass customization. But it was very important for us because it showed us that as designers, in this case, we could design a family of objects by designing a code, by having an idea and encoding this, and having other people participate in co-creation with this code. So all these tables here, you can see, easily belong to a family of tables. So we're not losing any authorship by delegating the form actually to someone else, while in classical understanding of design, you would say the designer is mastering the form, right? And in this case, we're mastering this design system, which produces a form. So it's a different state of action.
Okay. So this table project, this was 2002, and I mean this looks like it's a very long time ago. This phone looks prehistoric technologically, and back then we were doing it was a very beginning of our practice. We were doing competitions, having the time to do such open-ended projects, ending up with this rather ironic, but also very critical sort of project to, what was the discussion back then. And then just a few years later, this is now 2006, we're still, trying to explain where we come from or how we ended up being, we're discussing before, the robot guys. What you see here is 2005, 2006. This is an artist's image. It's not the way we used a robot, but it's depicting the robot that we both when we were appointed assistant professors at ETH Zurich for, I don't even remember the name of the probably machinic processes in architecture, something like this. And this happened completely by chance because our track was not academic. We were building, we're practicing architecture, but being highly fascinated by what these things, these machines would mean to architecture. And so our decision has been, instead of there were potentially many machines. You have seen this CNC mill that produced the table. We said, no, we want to experiment with a machine that is completely generic. And then we ended up with this industrial robot. This is a machine that wasn't high-tech at all back then. This has been invented in the 50s, introduced very quickly in the industry, has changed completely the way we produce things in the late 20th century. It's cheap, it's a mass product, it's super robust, it's big. So there were all attributes that made it attractive to us to build architecture. What we basically did was to look at this machine, the champion of industrialization, of serialization, in a different way. Because we said this machine doesn't need to repeat the same thing over and over again. This is the way it was used in industry, still used in industry. But the potential of this machine is to do different things every time it moves. So it's potentially the machine that allows us to interface industrial logics with architecture that has always, subtracted itself to serialization, to industrialization. And what you see on this image, and this is important, becomes even more important later, but we all already had, this intuition that the machine alone wasn't be interesting. It had always been about the relationship between the human and the machine. And in order to explain how we think about this relationship, I'd like to make a short didactic example. This is a brick wall. Brick is interesting because we started then to use, when we started to use this machine, we needed a proof of concept. And we started with brick, although we had never built anything with brick. And to be honest, we were not interested at all in this material. From a classical architectural point of view, our access point to this material, to its fantastic logic, has been through the machine. Because we said we have a machine that can pick stuff, place it, pick and place. So pick it here, place it somewhere else. Let's see what this changes. So this is the brick wall. Now the next question is, how do we represent the brick wall? This is a matter of notation. There are many possible ways. Probably this one, just to draw it, is a very simple and direct one. But we all know that, for example, if you describe something for production, you will not draw it up for the building site, but there are much more powerful codes, cultural convention, technical cultural convention, like the concept of a bond type, that allow us to describe the end result through a process. So bond type, a stretcher, many people share the understanding of what this means. And this is not an image, this is a sequence of actions. And this is already very close to a program. And once you have this, term stretcher that you share, then you just need a few parameters, very simple ones. Think back of the table. So you need the size of an object, a brick or a type, and then you need a few dimensions, and then it's done. So you can describe in a very compressed way, in a simple way, what you want to a human. If you want to tell this to a machine, let's say a robot, a computer, then you cannot use the term stretcher, because machine doesn't understand, doesn't know what a stretcher is. But there is this notation here that is as simple, as possible, because it's just the basic control mechanism of programming. One of the basic ones that means looping, repeating something, where if you nest two of these things, one into each other, then what you get is a brick wall. So it's the exact identical description as what we have seen before. And now we would say, and then here it's where a robot kicks in. You could say, okay, this is uninteresting, this is banal, we are just automating something. So we are creating again a stretcher bond. But now comes the trick. If you look here at the last two lines, that have been added to this very simple algorithm. You know, everything above stay the same, has turned black. There's these two pink lines added that compute something. And from the variable name, you understand it's about a rotation. You know? And this is very simple. Doesn't matter now how it's computed, but what now happens is this for us is design, you know, because it's a human on this side that understands the logic of the material and augments, extends it, and says, okay, I have a stretch bond, but now I add something. And what now happens, you know, through this act of design is that what before could be communicated to the building site or to somebody else just with a term or a concept or a process, stretcher, or with an algorithm, you know, a very simple loop, now becomes a lot of data. This is what you see on the right, because each element has now gotten his own rotation, small a number, floating point number, you know, very, very detailed, too complex for the human to execute. But this is where the circle closes. The machine that doesn't understand what a stretcher bond is, understands very well. And it's the only thing the machine at this, you know, I'm talking about 15 years ago. Now we could discuss about new developments, but back then this was the machine, what the machine would appreciate, would understand, and would execute independently from concepts of complexity that are important for us humans. You know, for the machine, there is no easy or difficult position in space. They are all identical as long as they are in the reach of the machine. So we are able to connect directly the human act of designing, of making design decisions, with the machining act of building. And what is important here and to understand, and there I go back to this artist image, you know, what we want to, you know, leave behind here is this, you know, notion of competition, of antagonism between human and machine that is deeply rooted, of course, in 20th century experience, 19th century experience, to cultural experience about what machines mean to society. But we are convinced that by reconsidering this relationship, turning into a positive collaborative one, where we say, okay, what are the roles? What are the strengths of humans and machines? We can do things like this. And this is probably one of the first moments when this term, or when we felt that we would need a term like digital materiality that would describe what happens here. You know, because there's a thing that cannot be produced by humans, but it is clearly designed by humans, follows a digital logic, you know, but it's completely three-dimensional. So this is not, you know, 2D graphics. And it's the result of this, you know, a collaboration between humans and machines.
Good. So shortly after building such first prototypes at ETH Zurich, we were invited to participate in a building project, so we could apply it to architecture at full scale. This is the winery Gantenbein. It's a collaboration with Berthe Platzes architect. We were responsible for the design and the fabrication of the facade. So here, kind of design and fabrication were no longer separated acts, but actually they came very closely together. What you can see here, basically, you probably see it best in this animation, is how we designed this facade. We looked at this building as an abstracted container in a way and filled it with oversized abstracted spheres, which were meant to be grapes, but not in a depicted sense, but in an abstracted sense. We then looked at this container from the four sides of the facade and basically took this view into this virtual three-dimensional space onto the facade by translating these spheres into rotation of individual bricks. You see here this kind of dynamically filled volume. So again, we kind of delegated part of our design control to designing a process on how we would design this facade. Tune down the volume here a little bit. So here's how we produce the facade. You see the robot picks brick by brick, as Fabio previously explained. And he also, or she, we don't know actually, it applies the glue. And you see this particular pattern that's quite important. That's actually exactly the overlap area between two bricks. And since each one of those bricks is individually rotated, of course, the overlap pattern is different for every brick. That is something which can easily be solved with the computer and with programming, but actually for a mason, it would be rather hard to always put this glue at the right location without spoiling the next brick. You see here how traditional crafts, you know, and this digital craft come together. You see the installation, you see the reference in a way. And the transfer. And you see that only by this very slight rotation of the bricks, that's only up to 17 degrees in one direction or the other direction. So it's a very small rotation that in the sunlight, this creates a very strong plasticity. And you can also witness that the material itself, the brick, gets a very high presence by this design principle. So it's not the same as producing just a digital image, just a pattern. Although it is somewhat similar, but it actually exposes the material, the brick, when you go close, and you start to, in a way, lose the more pattern-like aspects if you approach the building. In the inside, you have also an imprint of these transformations. Here it was important that the bricks were put very closely together so that the rotation would actually start to close the gap in between them. If we would have put the bricks 1 or 2 centimeters more apart and you would rotate them, in the counterlight you wouldn't see anything. Why do I mention this? So even if we design with digital tools, it doesn't mean that we see everything on the computer screen. We need to make physical tests. We need to work with the material at hand and see how it works under different conditions in order to understand, of course, the architectural consequences of what we're doing.
So you see that this project with bricks is where material starts to meet the abstraction of data, where it becomes extremely central, also because the brick reflects very nicely light. Now, the next project we would like to show is similar to many extents, because it's again the addition of discrete parts as bricks are, but now it becomes structural, slightly bigger, and the degree of freedom that bricks the elements itself is given, and you can just place it differently in space. Here there is 1 degree of freedom, which is the length. We're talking about timber slats, 5 by 10 centimeters, so pretty fragile thing, but the length of this industrially produced constructive material part, architectural part, can be varied in the process. What you see here is a 2,300 square meters roof structure that is covering the institute's building, our institute, actually at ETH. This has been an incredible, again, a sort of a lucky punch chance to implement something directly from research into the scale of a construction of a building, thanks to many lucky circumstances. And what you see here is probably the only drawing that exists of this roof, and it describes it's a plan view, and you see here about 50,000 different parts that are aggregated in a way that looks very much or feels very much like it would be a textile, a fabric, And we like very much this image, although you don't never see it like this. It's it's a virtual viewpoint, but you see that there are phenomena like where this it's big trusses, 15 meters long by 1 meter 20, 168 of them, how they can stretch and compress depending on other structural parts, which are in most parts the columns supporting the building or supporting the roof, but also less important things like ducts that need to punch through the structures. And normally, if you have above the staircases and things like this, you get these dimensions very late, and then often they're just cut through a structure in a more or less ugly way. Here, what is nice to understand is that until the moment this structure is built, it's just it's just computation, it's just data, it's fluid. And until this moment where you decide for the production, you can stretch it. So the material can create openings to let parts pass through. Now here you see the basic component. This is a truss, upper chord, lower chord, and diagonals. But it can adapt. It can adapt to a specific situation. The material can compress, can stretch, can follow a specific surface. What you see here, it's the basic layers where you understand how it's built, how the joint, where the diagonals meet the upper or lower chord of the truss, how it's done. And here you see now the second element. This roof is 50,000 parts, different parts, doesn't matter if they're identical or different, and then nails, it's nailed together. There you see a little bit the complexity because this is hidden. But if you nail through these layers, you have to find unique patterns where to put the nails. Because it's done robotically, it doesn't matter where they are, but you have to decide as a designer, where to put them in order not to have conflict, And here you see how this adds, how complex it becomes. And here you see how, once you have this computational design that starts from dimensions, from an idea, from this truss that I've shown you, once you have this, you can start to play around with it. You can stretch, you can deform, but you can also optimize. If you think at these nails, normally in a normal project, you would look for the weak point. What is the worst case? And then you would just, dimension everything accordingly, just because you are not able to differentiate. What is completely, stupid. If you're able to differentiate, to look at where you need the material, this is a process that has been done here. It's pretty banal, straightforward. You just said we will, not adapt the height of our slats, precisely for logistical reasons. We will stick to 3 different heights. But with these 3 different heights, just by differentiating, we're able to dramatically reduce the amount of timber that you would need to satisfy the worst connection. And here you see the process. This again is, the robot is slightly bigger. but basically it's doing the same thing. What happens here at the beginning, this is new, this is special. This doesn't happen with the bricks. You see this part is custom cut at length. But from here on, it's exactly the same. And instead of, putting glue here, the machine will just nail or shoot these nails at the right position. And these are all existing industrial processes. The only missing part that had to be developed here to make this construction, this structure possible was the computational workflow. Also to be able to communicate with the structural engineer, because this is not a thing that you can draw up and then give to the structural engineer, 50,000 parts. How would you want the structural engineer to model them or to, you have to agree on an interface that allows you to go back and forth, back and forth, back and forth until everybody is satisfied. And then from here on, it's the logic of prefabrication. In timber industry, this is normal. These parts, custom parts now get pre-installed, sprinklers, power lights, all these things get introduced in the truss here in the shop. And once they are complete, they are trucked to the building site, craned, and you see here the relationship between data and, humans and machines. You start with 50,000 parts. Imagine these parts on a heap. You have no chance to deal with them. But in the shop, through this prefabrication process, the complexity is reduced down to 168 parts that come to the building site. And then it's extremely, extremely simple here. You just place, put a few screws, you fix them, and you're done. Yeah. And you end up with this, strange again construction where data and light and material start to intervene and overlap. And one important characteristic, at least for us, is that it's one material system that does it all. So the structure is also, the architectural finish underneath. It's containing all the technical systems. It's at the end of the day extremely, extremely simple as a system.
Good. You've seen how something like bricks, timber slats, etc., start to become, in a way, almost like malleable materials. If they're treated digitally, if they're customized, shifted, rotated, cut in a bespoke manner. And now we would like to go to another category of materials. So we dive a bit closer to the material aspect of making. And we were, since the beginning, always fascinated with truly malleable or soft materials, which are partially used in architecture, but they always resist a bit the traditional ways of fabrication. So here there was a first experiment, a semester which we did with students called the foam semester, where basically we put polyurethane foam onto the so-called end effector of the robot. So the robot had a nozzle with which we could dispense this foam material. And the property of this foam is that first it's being put out in a thin line, but soon after it starts, to expand, to foam up. You can see this if you watch a bit this video. You can witness how the older parts of the material, the parts or the material that has already been deposited earlier, starts to foam up, so that actually the material itself is not a homogeneous material, but it's actually a material with age. And there's actually different materials with different or the same material with different ages on this panel. And you start to understand that, in a way, the temporal process of the robot laying the material and the material self-formation process start to overlap. And it starts to become quite complex as a design matter, and also quite intricate to see what you can produce here. So you see how this slowly foams up. I'm going to jump now, for sake of time, to the finished panel. And you see how extreme, in a way, these formations get from this simple material process. So here the self-formation of the material is creating the form. And the students, they were a bit underwhelmed, right? Because they designed what's here, for example, on the left, right? And they expected, you know, to get a grid, you know, with certain precision, and they got what's here on the right. And so it took a while, right, to make the shift from abstraction, you know, from geometry, and we're very used to actually design in geometry in architecture, to the actual material process and the understanding of that process, and understanding that when I'm drawing something, it's literally only an abstraction of the, in this case, the temporal process of laying this material. It's in this drawing in the left lower corner that you can see there is some exception there. This is the start and the entry point where the nozzle starts to lay this grid. So the students needed to learn that they design in time. Then some students started to explore this. For example, this group, which laid its their foam patterns in 2 passes. The first pass, the first pass creates a rather flat layout with some pockets, and the second pass crosses in diagonals, kind of diagrid structure, which then captures the material, which runs off the first layer of material and produces this captured material to foam up in these pockets, which were laid by the first process. Since I used to work with Greg Lynn, I always am reminded of the embryologic house, for those that know this project. So this is created here by the material process, these particular shapes. So I think it's pretty interesting that you can produce or design with the material, that you can actually have the material design for you. And it's also interesting that if you do this with, for example, digital processes, that you can still do something in a way repetitively. So such a panel, although it has a high degree of variance, you could actually repeat it. So you could also have certain levels of control and also let go of certain controls.
Okay, because this level of control wasn't particularly good, and the material is really an ugly mess. It's you know, this 2-component stuff. We decided to abandon it pretty quickly, although it's you know, extremely challenging and beautiful to think about what happens there in this radicality of these 2 temporalities that overlap and interweave, so on. We then decided to go to a you know, much simpler material, sand, that is not less fascinating, but simpler and cleaner and you know, easier to work with. Sand has fascinated many people. I think you know, probably everybody knows the studies of Frei Otto and so on. But what we were interested in is in the processing of this material that, like the foam, would have a, you know, a behavior, a way it forms naturally, so giving you a, you know, a resistance to formation, but at the same time also doing automatically, you know, sort of material computing things that you would not be able or would not design. We were interested in coupling with it with this automatic deposition. So having the machine going through space and you know, depositing. So just opening a valve and closing the valve. And as you probably have noticed or not, with feedback processes. You know, this now it was what comes in here. There has, you know, there was this small laser, this small dot on the sand, because, you know, how much you have deposited is not so clear, because you just open a valve and close it. And it's not so important as long as you can, in this case, for example, go back and measure what has happened. And then the next step, you know, is derived by this. So you really start to work in a processual, by designing a process that can be, you know, simple or complex, and produces extremely interesting material formation. Again, here the question is, or what interests us is, what is, you know, the design act, or where do we, you know, or how do we interact with such complex things that to some extent are beyond what we can anticipate, you know, are beyond what we can simulate, or probably we don't even want to simulate this thing, because it's, you know, the process of discovering, you know, of having these things emerge, and then the process of understanding what happens when, and starting to instrumentalize these things towards design. That is the really interesting point, you know. And these things are also fascinating because they are completely ephemeral, you know, and they are recyclable. You know, we'll see this later on with other projects. Here, the follow-up of it, although its processes we still work with students, you know, because on a you know, just intellectual way, they're extremely nice. But back then we looked for an application that would really justify, you know, the use of sand, and we created molds, reusable, completely recyclable molds, you know, that would were fixed. So first you had the robot depositing material. And this is a very quick, very simple process. If you compare it with, you know, production of form, if you would mill or cast or whatever, you know, this would be a nightmare in terms of cost, completely unsustainable. You know, here the only thing that comes in, it's a very thin 1 millimeter layer of latex that is sprayed on top of the sand here, in order to avoid, you know, the cast concrete to penetrate too much the sand. Then we have, you know, the casting of the material. Then this peeling process, you know, after the molding, you get this latex layer off. And then this again was student projects, three panels, large scale panels, you know, that are from the point of view of form, come for free, you know. So there is the minimal amount of energy and material that you could invest in order to create extremely complex shape that can be, you know, custom.
So then naturally the question starts to arise, well, you can lay foam, it flows, maybe it foams up a bit. You can lay sand, it forms, you know, certain angles. Well, how do we get actually architectural? How do we can actually build? Can we get vertical? And so we had, inspired actually by a science conference on jamming, we had this kind of vision that, or the question, let's put it that way, is it not possible actually to aggregate gravel in a way that when we put load on it, it self-constrains itself, it gets jammed. So imagine this like a traffic jam in a way. It's basically the particles block one another. And then if you release the weight on top, it actually unjams and you can reuse the material. So that was the basic thought, inspired, as I said, from this physics conference. And of course, this was not so easy because still if you get gravel, it does this. So it's just a widely available material worldwide. It's very abundant. It's very cheap in most of the places. But how do you get it to stand up? So we did a lot of tries. You see, we started to mingle these kind of particles with other materials with ties, with wool, with all kind of tension elements. Say, okay, how could this work? And then slowly over time, with many, many tests, we started to figure out, well, with the right dosage of gravel particles and string, and with some pressure, which is actually needed to constrain the system, so you see above this piston, we can actually achieve pretty slim columns. And you see here in the video, this is Skylar Tibbetts from MIT, who was collaborating with us on our project. So he joined our lab, and together with Petrus, our PhD researcher, we did many, many tests, and we found basically some first initial formula on how to build slender elements with these two materials. So gravel and a very, let's say, inexpensive recycling string, which doesn't need to be very performant. It just actually needs to keep the gravel from moving. And this was the first, let's say, slightly larger scale prototype and the first load test in the lab. So this was basically a cube, which we filled in a formwork. And you see here, I guess it is Petrus standing on it, whipping a bit uncertain if it would, fall, but actually it stood up to the load test. And we exhibited this project at the Biennale in Chicago. We developed this structure. This was an early prototype for it. So we built a structure that you can see as the basic characteristic that it stands on thin feet, but it has a huge volume on top, which creates the load, which is necessary to stabilize the feet. So this expresses directly what is the characteristic of this material system. And you see how beautifully it disintegrates if it falls. It liquefies actually. It goes back to its previous state. So I think for us, this is pretty close to fundamental research actually in architecture. It's about sustainability. It's about reversibility. It's about how to make processes circular. It's maybe not yet a full building system, but we wanted to try it. So in Chicago, we had built the system in such a way that we built this box into which we manually laid a layer of gravel, followed by a layer of string, which was deposited by the robot. And the string pattern, I think you can sense it here, is the shape at that particular layer. So it's literally a 3D printing process of this composite in this formwork. And then here again, another layer of gravel. In this case, it was a lighter gravel due to the floor load restrictions of the exhibition place. So it actually stuck a bit to the volume, as you can see here. So we dismantled this box. You can see parts of it already falling off. And then you can basically, just by gently touching the structure, unearth the more solidified jammed structure inside it. And this is how we exhibited the piece. I mean, the people were amazed by the structure, but they, in a way, didn't believe that there's no structure inside. So it's always, if you told someone there's nothing inside, and sometimes I was going there and touched it, and some gravel would fall off, people, of course, back off. It is, in a way, a scary thought, right? It's a number of tons of material which are standing there, right? And just are basically, their movement is frozen in time. And nice little details appear, like this little stone here on the edge. So it shifts a bit our apprehension for what details maybe could also be in architecture. But the nicest part of this project is that then afterwards, Petrus, our researcher, could just basically activate the spool and pull out the string out of this structure. And so in a kind of quite a dusty performance, the structure would unbuild and we would end up with the two basic materials from which the structure was built, which is string and gravel. We then later had the chance, I'm gonna forward for time reasons here, if it lets me. We actually had the chance, and was quite a courageous project, to do this in public space. We needed to convince an engineer that this is viable, and we found a courageous one. Not all engineers agreed that we should do this, but basically the engineer agreed that if we monitor the structure in a certain rhythm and we see that it doesn't start to shift, it's safe. If it starts shifting, over time, then it's not safe. So we could actually find an agreement, and also coupled with a number of load tests, so that we could build the structure. Here you see, of course, the roof plate does two things. It protects the structure from rain, but it also is the weight that actually reinforces the structure. This was now built from just ordinary gravel, like it's used on train tracks, etc. You see here the build back process. I'm not showing the fabrication process, but just the build back. So we lift off this steel roof, steel plate, which can be reused. And again, just a bit on a slightly bigger scale, we pull out the string. Until finally we have the raw materials, which we can take away with this wonderful machine here and reuse them. So we would like to show also this other side of architecture now, right? Because the build back of architecture should become our new design topic. We need to take care of it. We need to also appreciate the aesthetics of it and start to understand it as part of an architectural cycle.
Now we've seen this gravel projects. The fascination there is, or the motivation is this radical, sustainability. Proposing a material system that can be literally rewinded like a movie. You go back to original state. You have no degrading of anything. You just start over, reusing it or building something new. Now, the next project I'm going to show you is addressing similar topics, a similar motivation, but with a complete different material system. Because here it's not about self-aggregation. Although it looks like here, this is, big stones, heavy stones, 1.5 ton average, that are mixed with, you see it there, with rubble, demolition rubble, concrete parts, and so on. And the approach, which is, opposite, is can we, with really big machines, excavators, start to do what humans did for thousands of years, to stack very complex stones as found, maybe with minimal modifications, so building of dry walls that would be highly performant and highly sustainable, because there are materials is sourced on site, but do this at the scale that we cannot handle. And in order to do this, you have seen it in the movie, we need first to acquire information, so to scan, be able to understand how what the form of this parts is, in order to be able to handle them, and in order to be able to, what you've seen here, to find the good location. And this is a very complex logistical and computational problem, because if you would have at your hands all the stones of the world, then it would be pretty simple. Then you find the perfect solution. But you always, and this is the same thing that as a human you experience if you do it, manually. You always have a limited understanding of the problem. in a particular situation, and you have a limited amount of parts that you can grab or that you can use. So it's an optimization problem. And we have been, let's say, this has been PhD work done by PhD students of us, but also, of course, with roboticists for other PhDs at ETH that were looking into this automated excavator that could, you know, process this data and then grab the parts in the right way and deposit it at the right place. And we've been able to build extremely, you know, slim and performant parts, walls, retaining walls, things like this with this machine. You know, you see here, that is very beautiful, but also, you know, speaking about you know, a different use of our waste that we could possibly make out of our waste if we are able to understand these parts and to reposition them in a way that makes sense. And as a demonstrator of this PhD work with a company or at the site of a company that does recycling of buildings, we have been able to do this very long retaining wall with this technology.
Now we move to this material. That's earth or clay. Basically, earthen materials were also a fascination for us for a while. We didn't really know so much what to do with it, but we had an idea which we wanted to try, which was actually shooting material. And there it seemed like earth would be a fantastic material. So if you think in terms of fabrication concept, classically, a machine that fabricates something is as big or bigger as the part that's being fabricated. So what we were conceptually interested here is, can we have a machine which is smaller than what is fabricated and actually throw material, that's why the project is called remote material deposition, at the location where we would like to aggregate it. Was a bit of a crazy idea, and we tried it at the Zitterwerk St. Gallen. And here you see this apparatus. So it's basically a robot that can guide the shooting mechanism. You see that here. And we prepared these clay projectiles, and we shot them in a ballistic curve. And you know, these ballistic curves, they're pretty calculatable. And we installed a scanner system, where we could from time to time scan what we had been throwing. And you can see we were able to build a structure which was about 10 by 10 meters with a height of up to 2 meters. So I think this was the highest point. So this was higher actually than myself in this case. And this was also actually a very slender part, because in the direction of where you would shoot the material, the precision of where it would land would be very, very good. If you had a wall which went in the other direction, it would start to blur out due to some, you know, random forces or sticking, etc. So it also had this particular expression in the material system, which we liked a lot. You see this deformation of the projectiles, which expresses itself. And here you see such a projectile coming from the landing point. So it again has also a performative aspect. Yeah.
Have you seen it? This last project, it's again, it's about the control, and also how much control can you pretend to have or force a material system into, or what is even, you know, interesting. And this project there, you know, its beauty is really the fact that these things are completely out of control, but at the same time, in a, you know, at a statistical level, they allow you to control form, but still you will be able to read. If you look at these formations, you know, it's really speaking about the process, you know, because you see through the deformation of the single parts, you see how they have, you know, impacted the pre-existing, the other parts that were already there, and so on and so forth. Now, in the project I'm showing you right now, it's stepping back at least one step, because this was a commissioned work, was the outer shell of a sound acoustic lab. So we needed mass, the client needed mass, but at the same time it was in interior space. It had to be extremely slim. And so the brief was to build a rotunda with 11 meter of diameter, 5 meter height, with the minimal amount of material. And what we have done, the two things. So it was clear that we could not shoot this. Yeah, we didn't have enough control of this, although it would have been beautiful. But we would have to find a shape that would stabilize. So this undulation, you know, makes it stiff, because it's at this dimension, 5 meter high, it's 15 centimeter thick. This is paper thin. If it wouldn't be undulated, it would just collapse and break. And we developed a process now with a machine that, instead of throwing this, it's the same amount of material. It's this cylinders. Now the machine would sort of press it into position. You see, the big challenge has been to, you know, how to segment this thing in order to have it buildable. So have the machine being able to address a certain range of operation that then is moved from time to time. And this will also be, you will see it now here. This will also be the joints that remain readable in the final piece, you know. This is now about a lot of control at the level of the placement of the material, but still, because clay is a difficult material, so it shrinks a lot. You have then, you know, these patches that become visible, so it resists this digital perfection, you know, that you could read into it. It becomes extremely, you know, sensual and physical and material.
Good. So now we ventured quite a bit into different material system. I think it's important, particularly for our future, to start to understand these materials and maybe work with them in different ways, and also explore, you know, the cross section between these different material systems, which can also be malleable material systems, and digital processes, because maybe the ways that we build will change. Now we would like to come back a bit to full-scale architectural projects, which of course have also pragmatic limitations, but we would still show you how we try to push research into architectural building projects. This project here is a particular case, because here we actually had 4 research projects which we brought together on one architectural project, because it's rarely the case that you only have one material system that you can create architecture out of. So here, basically, this was the first project where we achieved to build an entire, let's say the entire structural system of this project was built with digital fabrication processes. This is a fully, let's say, approved building by Swiss building codes. So this for us was an important step, because basically we go beyond the arts installation, beyond the prototypical, beyond the experiment, which we love and like, but at the same time, we also want to say, you know, this is for real. We can build buildings which are inhabitable and usable So this is a guest house for researchers. By the way, the building below is by our architecture office. It's the Nest Research Building. It's a building onto which you can build buildings, but I'm not going to go here. I'm going to stick with the research for a moment. So here are the different research projects which make the core structure of this building. And I'm going to go through from bottom to top. So we start with this mesh mold wall. So this is the central wall on which basically the upper stories are standing, which is supporting the upper stories. Here you see it's the first time that we built on site with the same robot that Fabio has shown before that built the clay structure. So this robot is here used to build this mesh. It's called mesh mold. It's a mesh that is at the same time the reinforcement of a concrete wall, as well as the formwork for that concrete wall. So the research is actually on the one hand side on how to build such a doubly curved wall directly on site. We see it here, this beautiful mesh, but also how this mesh can directly be the formwork so that we actually can build with concrete without using formwork, which is again very good in terms of sustainability, but even economically, it is interesting. So this mesh is basically filled sideways. This is an earlier version. Now there is a spin-off with a slightly different process, but this mesh is basically filled sideways with concrete. And due to the size of the mesh and the correlation with the concrete that is put in, the concrete sticks in this mesh and it doesn't basically flow out. And you can see it's a very thin, actually, wall. It's, again, has this shape so that it can actually structurally stiffen the building while creating the main spaces in this project. Then there is another project. These are these little facade columns. They are not load bearing, but they're actually just taking the wind loads from the facade. This process is called smart dynamic casting. It's a very clever project developed by our PhD here, Ena Loret. She's now professor in Mendrisio, where basically concrete is filled in a small slipping formwork, and it cures exactly at the moment when it's at the bottom of the formwork. And so this formwork can slowly slip up while the concrete is always able to sustain its own weight. So it basically, it's almost like an extrusion process for concrete, where again, you don't need a complete formwork and you can change the form while you actually do the slip casting. So here you see these slender elements. They all have a varying size. And on top, I'm not going to explain the project, but this is the so-called Smart Slab from the group of Benjamin Dillenburger. Very nice piece, which is actually built with a 3D printed formwork. Quite an elaborate process. But here you can see that building with concrete doesn't need to look like we know it, because there's certain stereotypes or ideas about how a concrete or an exposed concrete building looks like. But as soon as digital fabrication processes come along, and we can reinterpret also these conventional material processes, and maybe the expression of these processes start to change, hopefully in a most sustainable way, because as we all know, concrete is a bit of a tricky product with respect to CO2 emissions. So you see again these qualities, which of course are visually very appealing, but also can have acoustic qualities, etc. On top of this now concrete base or table structure sits a timber structure that automatically adapted to whatever would be built below. So this is kind of computer generated, this structure. And we built this in our robotic fabrication laboratory. You see here 2 robots collaboratively placing timber elements. The structure was made such that we always have a stable structure. So here the robots place the corner elements first, so that the corners are kind of triangulated, and then start to place the beams and the other elements in between. So actually, I mentioned that to say that robots are not only tools for automation, but we also need to rethink how we construct, literally in terms of sequence and what goes first, what comes first, what comes after, when we build with robots, and that also has an architectural expression. This was complemented with the translucent facade. That's a membrane filled with aerogel, around 10 centimeters of thickness. This pattern, which you see, this marble pattern, is actually the fill-in of the material. So it's again a material expression. And it's a very nice space, very well lit, doesn't have a lot of windows. It's literally just translucent, has its own qualities, but it uses the fact that this timber structure is spatially built. It stiffens itself out, so you don't need stiffening plates to actually stiffen out the structure. Therefore, a membrane was enough, and this creates the expression of this building.
Okay. Now we're almost done, but we have another two projects, I think. This one I'm going to show you is again a brick project. 15 years after the winery. It's again a winery. It's in Greece, and it's a strange story because we got a phone call or a mail from a winery in Greece, and they basically wanted the same thing we've done in Switzerland in 2006. And we thought it through, and we concluded that this wouldn't make any sense, to produce robotically prefabricated brick elements in Switzerland, ship them to Greece, a few years after the financial crisis, just mad. And so we politely told them that we would not like to do this, but they insisted. And then at some point we started to look into the job and found out that it was actually very interesting, because this is the finished project. It was again about a structure, so a found object, an objet trouvé, like in Switzerland here. Here in Switzerland, it was designed by good friends of us, by the analog architect. So it was this steel frame, steel concrete frame. Here it's just found because it's a ruin. It was designed. It's a classical architecture without architects. It was designed and stayed there because they ran out of money for a while, and now it was again about interpreting this thing and completing it and filling it up. And there were these correspondences that made it attractive, that almost cried, to find the solution. And then we find a really interesting solution that has been to implement a completely new technology that to some extent could be now interpreted as being a contradiction, to what we did 15 years earlier, which is augmented reality. So here we said we will not use robots. We will not produce it off-site, but we wanted to build on-site. We wanted to build with masons, local masons with local bricks. And we wanted to use this to get much bigger. So this inserts there, they're 5 by 5 meters. So this is not something that you could segment or transport or prefabricate in any way. And if we go closer, we would also start to use a mortar, to build this wall. A thing that we had to exclude in the first experiment, just because it was not feasible with a machine. A robot could not use mortar, and then we decided here to go extreme with the use of mortar, really to make it, you know, have it appear as sort of the counterpart to the brick, have it also have these brick courses, you know, going up and down. And the technology we applied was back then very experimental. Now this is also, you know, moved into a spin-off of ETH. It's another group. It's in robotics, which starts to now develop these processes specifically for timber construction industry, where they have the sort of low-hanging fruits. If you know where parts are in space, then you can close the gap between the data space. So what normally only the robot or the machine can interpret in an efficient way, and the human as a designer, and then you get this very hybrid situation. So if we go think back at this very simple dichotomy between the designer, the human, and the machine that I've shown you at the very beginning of the lecture, where we started with, you know, here it gets much more complex, because where do you put such a process where the human and the machine are really start to be to become one? What you see here is as it worked back then. You had, this is 4 years ago, we had a screen on the building site that was showing to the mason that is placing a brick. So the first placement is pretty intuitive. You just place it, and then by tipping, you bring it into the right position. It's what you see here. So there is this augmentation of the human, you know. So now we're not automating the human, we are augmenting it, just giving the human that, you know, is mastering a very, very complex process, an additional tool to you know, allow him or her to do things that wouldn't be efficient, you know. They would be possible, they would be completely, you know, crazy and efficient without these tools. Yeah. Here you see now the final. And what was very interesting for us to, this was also PhD research, thesis that now is concluding, Daniela Mitterberger. What was very interesting to understand is by interviewing then the masons that were working 3 months on this building site, how they would understand, how they would relate themselves to this augmentation. And at the end of the day, you could conclude that they were extremely, you know, fast in adopting this thing, and also extremely positive and proud about, you know, how this would increase the potential of their, so not questioning their craft, but increasing its potential.
Good. As a last project, we're going to show you Semiramis. So this is really, in a way, part of an urban development in Switzerland. It's in the city of Zug. It's in a former industrial site of, I don't know if some of you know, there is a brand for appliances called Zug. So this is basically their production site, and they do quite big urban redevelopments there. And they came to us because they wanted something which is a strong sign, you know, towards the future. And originally was more something like, you know, a small installation, maybe a little pavilion or something. And we were looking at their master plan, and we saw that, you know, they were building, you know, tremendously high developments there, really massive buildings. And so we said, you know, if we want to do something here, we're not saying it's not about size, but in a way, this needs to be visible also in this massive context that you're building. So therefore, actually, we started to create this concept of a very vertically developing garden, one which is not accessible by humans. So this was basically our condition. We said, you know, we're going to plant up there. Animals can live up there. You will not go there, but you will see it, right? You can't touch it. So this was basically the design setting. And what was particular, Fabio has shown you before that we use this kind of, we're very interested in the dialogue between humans and machine. And here we expanded this to machine learning. I mean, now, you know, the news are more than full with it, what you can do with machine learning. It's very hip. But I've been working on the topic in 2018 in my sabbatical. And so we took this topic and we said, okay, how can we design with this? Can we actually design with machine learning? And there's one interesting thing with machine learning. We can actually start to reverse processes. So what we did here is we took basically 3 simple parameters. So this is like a very basic experiment which we did. In this case, it was like the surfaces, with how many surfaces or how many square meters get sun on such a structure in average days, how many square meters get rain, and how big are the surfaces of such a structure. These were the parameters which were learned by a machine learning system over 500,000 of variations of such structures. And then we could reverse design basically the structure. So here you see an example. You see here, for example, if I can read it, how we slimmed down the number of square meters, and suddenly the system proposes this slimmed out structure here. Here the rain occlusion is diminished, so meaning that the shells should be wider apart so that more rain goes onto the shells. And so this system, which we created ourselves, so it's not foreign to us because we made it, now gives us propositions on how this could look like if we wanted different change those parameters. And it always gives us plenty of options to look at. And so we challenged a bit ourselves, okay, can we design with such a system? Do we feel alienated by it? Or is it exciting to actually design such a system and then build with it? It's in a way, you know, what we did with M-Table, but with a bit different technologies. And that's what we did. And we actually designed with the system, and it was quite pleasant to do so. It wasn't the easiest path. It would have been more simple, obviously, to do it on a napkin. Probably it would have been equally performant, I need to say. But it was interesting experiment for ourselves to see if we could delegate part of this decision process and what this means. I think one of the most important findings of this part of the process was that we were finding, by the sheer number of possible solutions, we were finding solutions which we didn't think of, and we found characteristics of the final configuration, which is this one, which we liked, which we would have designed if we would have designed it by hand. So the interesting thing is exactly what differentiates this design from a design by hand or on a napkin, or however you like to do it. Then another part was the fabrication. This was the first time we used all the 4 robots that we have in our robotic fabrication lab. It was a bit of a challenge to ourselves. Basically, it's a timber shell structure, which is assembled in this mode. So these robots drive together these timber plates, which were pre-cut, CNC pre-cut, precisely in space. So you don't need a framework on how to position them in space. And then there is a special connection system. It's a glue which you can fill in into the gap between those plates. And this creates a fully continuous structural shell. It's actually quite a material efficient system. If you look at it, you see how thin it is. It's like a folded plate, especially folded plate. It would, of course, be better if it wouldn't even have glue, but I would say it's only a minimal amount of glue. And like this, then these pieces were assembled with some additional elements, and they were brought onto steel columns and assembled into the structure. This is shortly after the erection and the plantation. It was still a bit underdeveloped, not quite the jungle that we imagined, but more and more it starts to grow. It's actually quite full right now. This is not the latest state, and it develops quite nicely. It's very beautiful to see from underneath, because if you walk around this structure, it always looks highly different. It's very similar to what I've shown you with the Guggenheim project, that the light creates this diversity, which in a way also reflects the diversity that was created with this machine learning system. Now you see currently around it, it's quite a void area, but this stands right in the center of this urban development. So now every building, which is now designed by design competitions, in a way starts to react to this. And we've already had now a design competition, which Guggenheim Swiss office had won. And actually they took reference to this structure and also created kind of parts of their facade designs, etc., which were responding with vegetation on their facade. So in a way, it's an interesting seed, hopefully, for sustainable development. And yeah, with this, I would like to conclude. We filled the entire time with our lecture so that there is no room for questions, but I would still like to invite you to ask questions. Yeah, we started slightly late. So if you still would like, you can, of course, feel free to ask some questions. Thank you.